time to move on to our next speaker. What I would like to do is move on to Martha Morrissey, who's and welcome Martha to the stage. Martha has previously worked at Maxar, formerly known as DigitalGlobe, and that's one of the premier providers of satellite imagery data, for those of you who aren't familiar with that, and is currently a machine learning engineer at Development Seed. So Martha, please come on up, turn on your camera and microphone, and we very much look forward to your presentation.
Hi, thank you so much. I'm really excited to be here. Let me share my screen. Yeah, hello. I'm Martha, and I'm a machine learning engineer, as I was just introduced by Kyle. And today I'll be talking about Development Seed's work mapping high voltage infrastructure using machine learning, satellite imagery by keeping humans in the loop with this process. Our combined method of using machine learning and satellite imagery allowed us to map about 33 times faster per square kilometer when we're trying to trace out the electrical power lines and power towers as well as substations. But kind of taking a broader view, why do we need an accurate map of HV grid infrastructure? It's really important to have an accurate map because one of the sustainable development goals is everyone's right to affordable, reliable, and sustainable energy. But to first make progress towards achieving that goal, we need to understand where and how the current electrical grid looks like in a given country. And having an accurate map of that is actually pretty tricky. A lot of countries lack an accurate countrywide map of this information. It could be out of date, or it could be missing key structures. And sometimes there's regionally specific maps that are accurate, but those are really hard to aggregate up to a countrywide level. And currently a lot of them are made by hand, so it's not really, and it's very manual, so it's not efficient to scale up. So we partnered with the World Bank to have a pilot project to see if using machine learning and satellite imagery, we could develop countrywide high voltage grid maps quickly and cost effectively. The 3 countries we first worked with mapping were Pakistan, Nigeria, and Zambia. So this is kind of an overall outline of how our pilot project worked. We first curated training data and matched up the presence of towers and satellite imagery. Then we trained convolutional neural networks to identify HV grid infrastructure. And then what's really exciting is we ran inference over these entire, all 3 countries, which was over tens of millions of tiles of satellite imagery. And then we come back together with humans in the loop and manually go through and validate the predictions to create a map of towers, substation, and power lines that's added back into OpenStreetMap. So this is kind of a more detailed, but still a high-level overview of what step 2 in that process looks like, our training pipeline. Our training data, we matched up the labels and satellite imagery using an open source tool that Development Seed has created called Label Maker. And then that data is put into a binary format called a TensorFlow record, which is faster and more efficient to map with. And then we go and we use that data in different types of traditional classification models, as well as object detection models. Most of what I'll be discussing today is focused on our classification model work, since that's more fully fleshed out. But we have been doing some work to get more precise locations of towers with object detection. Our training is facilitated with open source tools like Kubeflow, which is great. It's really scalable and makes training these large data sets fast and very efficient and very reproducible. And then finally, when we have our best performing model, we Dockerize it and we use TF serving to help facilitate our inference. And some of our initial classification models, the Docker image for inference is publicly available on Docker Hub if you're interested in looking at it. So going back to the training data, we modeled with the 3 countries, again, Pakistan, Nigeria, and Zambia. And our training data came from a subset of each of these countries, about 1% of the total land area we got data from. And one limitation of our work is that our training data, well, it came from 3 different countries. Within each country, it was in a pretty homogeneous geographic area. So for future work, we're going to try to get our data set to be more geographically diverse within a country. So this is an example of some of the classification data the model saw. For the classification model, it's at a per tile basis. So the model is trying to predict the presence or absence of HV grid infrastructure. And we see that the towers, depending on the background, they're easier or harder to see even just with the human eye. The tower in the leftmost tile is in a desert region, so it's really distinctive. There's not a lot else besides the tower and the power lines. The middle and right images are of the towers in farmland, and these are definitely a little bit trickier to discern, but still possible with the human eye. We were working with tiles at a zoom level 18. So they're about 100, they're square tiles and about 150 meters on each side, and each pixel in the tile represents about half a meter. For object detection, our training data is more precise. It's not just at the tile, it's at a specific bounding box around an HV grid infrastructure like a tower. So this training data is more manually intensive to generate because you need the exact bounding box around a tile, but it is giving you more precise results. You can narrow in. And these are some examples of predictions over the validation set during training. The left, in each pair of image, the leftmost is the model predicted confidence score, as well as the bounding box around the object, and the rightmost image is the ground truth. So sometimes the model does pretty well with towers, but other times it gets confused. But these are all examples of where the model is performing well, which is exciting. But going back to our classification models, once the model is trained and is doing inference for each tile it sees, it produces a confidence score indicating the presence or absence of HV grid infrastructure. Then those scores are thresholded above a certain value to turn into binary yes or no labels, and then the yes labels are visualized on a map. So we can start to see these distinctive lines show up, and that's a good sign that is following the geographic pattern of power towers and power line infrastructures. So this is looking at the entire country of Pakistan. For some areas, we see these clear lines, and that's really exciting to see. That's an indication that the model is predicting these towers, but other times we're seeing these darker blobs, and that's an indication that there are some issues with false positives. But again, despite the issue of false positives, having humans in the loop really address that situation because we're directing humans where to look. So we're still speeding up the overall mapping process, even though people have to go through and reject these false positives. So going into a little more detail about how we have humans in the loop, we have professional mappers working with the model output GeoJSON predictions with common OpenStreetMap tools. We started a mapping campaign and tasking manager, which allows multiple people to map the same data set at the same time, but divide the data set into unique areas. So one mapper is responsible for specific tasks. To break up mapping a whole country for one person, that would be a long time, even with the search space reduced from the outputs from the ML model. And then the data is edited in JOSM and eventually added back into OpenStreetMap. So this is an example of manually tracing the infrastructure. The orange boxes are predicted power towers, and then the red lines represent tracing the HV grid power lines in between the towers. And we see that with the three that just appeared on the screen, not all of the towers are being captured by the model predictions, but that's okay. The model has directed users to the correct area, and since the towers occur in a line, it's pretty easy to just scan the surrounding area and make sure there weren't any mispredictions, or if an orange box is a false positive, to not delineate that a tower is present when it's not. So to kind of override what the model is predicting, but the goal is to have humans and AI map together. Mapping in a countrywide scale is a really challenging task for humans to do. But with machine learning, it's become possible, but we see with this results, it's not appropriate to just have the machine learning models output the predictions and those are taken. There needs to be humans in the loop for validation as well. And this is just another example. The yellow is what the map looked like before, and the green is what the map looked like after, with the combination of validated machine learning predictions added. So for Pakistan, Nigeria, and Zambia, these graphs show the total number of infrastructure in terms of substations, power towers, and kilometers of HV grid lines that we added as an end result of our work. So yeah, this kind of shows in the beginning the dark green squares is what previously, sorry, the dark blue bars are what previously existed, and then with the light bars is what we were able to add with machine learning outputs. So briefly going through how we run inference at a countrywide scale, we have an open source tool called Chip and Scale, which is a collection of AWS Lambda functions, SQS queues, and TF serving images to facilitate running tens of millions of tiles worth of inference at a cost-effective and quick manner. So for this work, classification model inference runs about 3 million tiles per hour, and the cost of this is about $10 per million tiles, which is pretty cost-effective. We ran inference for the 3 countries in about 31 hours, so the cost for the total inference run is a little under $1,000, and the cost ends up being reasonable because some of the functions that need to run on GPU, and that's specifically when the images are getting sent to the TF serving image, but the initial downloading of the tiles from a TMS server and the post-processing and putting the inferences in the database don't need to run on a GPU, so those functions just run on a CPU, so it's a lot more cost-effective. We've also done some new work for how we run inference at scale, building on top of Chip and Scale. We have a tool called ML Enabler, which provides a UI on top of Chip and Scale. It still has all the AWS resources bundled together, and inference runs the same way, but it's more interactive and allows for users to validate predictions within the tool, have automatic integration with common OSM mapping services, and it also keeps track of different versions of models and different versions of predictions. So you can kind of think of it as a GitHub of models. This is an example of object detection predictions within the ML Enabler tool. Since this is an object detection model, the geographic output is a bounding box around the tower, and then you can see here this bounding box was validated, and the model confidence that this predicted bounding box contains a tower is about 66%. With ML Enabler, you can zoom in and out to see predictions within your area of interest. We see 3 towers following a natural line structure, and all of them were validated and true, which is exciting. Yeah, so some next steps. We're interested to improve our workflow, particularly around maturing our object detection predictions and improvement to those models. We'd also like to explore using SAR data in addition to the RGB imagery. We think that using SAR data could help correct these false positives, especially in urban and urban areas and farmland areas. We also, especially for the object detection models, want to do more post-processing to reduce false positives, to take advantage of the geographic structure and the kind of uniform distance between the different towers. And most importantly, we're really interested in collaboration and applying this workflow and working with other people in the field to help address other energy use cases. Yeah, thank you so much.
Thank you so much, Martha. Let's jump in for some Q&A now, and we have a number of questions that have been asked. So let's start off with this one here. So Joseph Silvers asks, could you speak to concerns or considerations of data security with respect to these aspects of critical energy infrastructure?
Yeah, I can try. So this was a pilot project with the World Bank. So I think that they are really thinking about data security and mapping the critical infrastructure. And I think having an accurate map, again, is really important to achieving the UN sustainability goals. And there is already similar infrastructure data publicly available in OSM. It's just not fully robust. So we're adding to data that was already publicly available.
Yeah, because it all builds on the OSM platform for storing the data and kind of for where the data are eventually housed. Is that right?
Yeah,
Okay.
yeah.
Great.
And they already have HV grid infrastructure data there. It's just not necessarily complete for a given country or area.
Sure, sure. Another question here: Did you encounter any challenges with the quality or accuracy of the ground truth labels from OpenStreetMap?
Yes, that's a great question. And we did. So we didn't just simply rely on OSM data. We had development seeds data team using OSM as a guide. But our data team consists of engineers and professional mappers that are going through and validating the predictions. And if there's inaccuracy in OSM for this project, they were also correcting those inaccuracies. Our training data didn't just start with pulling OSM data. There was a human looking at it and curating, because if you start with bad training data, you're going to end up with a bad model and bad results. So training data, as I'm sure you all know, is super critical to get that right and get that as accurate as you can before you start feeding it into a model. So we have humans involved kind of throughout our ML process, starting with making sure the training data is looking really good and aligning well with the imagery, and then going through the process and validating our predictions.
Awesome. So you cleaned up the existing OSM data before you used it in your models.
Exactly.
Great. Another question here: do you have a sense of how many person hours this took to kind of facilitate that human in the loop component of the work? How time intensive was that with respect to these countries that you've done so far?
Yeah, so it does vary a little bit by country, but without any guidance from an ML model, our data team was able to map less than 50 towers per hour for the fastest country. But when we go back and add this model guidance prediction and narrowing in on where they can look and giving them a specific tower, a specific tile that might have a tower, that prediction speed increased to about 150 towers per hour.
Wow,
but it does kind of vary based on the region.
Sure.
But it's a significant increase.
That's fantastic. And a follow-up question on this, well, based on what you were just saying, do you think it's, given that what you're doing here, is it feasible to think about doing this year over year, several years using historical data, or have you even already done this?
We have not done this, but I definitely think it's feasible, and I think that would be a great thing to investigate. Probably the hardest part of that is getting or purchasing the imagery to go back and do that, but the model is equipped to take in a new imagery source. And that'd be really, really cool to look at the change over time.
And do you have access? I'm trying to follow up on part of that question there. Do you have access to kind of historical data with that? Do you know of, or is that something that you would need to get to make that a possibility?
We would need to get that to make it a possibility. Right now, this model was trained on imagery from Maxar, so it's pretty high resolution, but I know that there are publicly available data sources. They're just lower resolution, so I'm not sure. You would probably need to work with a new model. And this work was a project with the World Bank, so that's how we got the imagery through a partnership with them and Maxar. But I know Maxar has the imagery going back. They just don't give that away. But that would be really interesting if anyone had the means to purchase a time series of imagery or look at upsampling publicly available imagery like Sentinel or Landsat.
Well, and we had a sudden surge in one of our questions here, so I'll end with this one. So is the ML algorithm able to make use of the fact that towers are connected to each other, can only be so far apart, and start at a generation facility, or does it just look for the towers without considering that information?
Yeah, that's a great question. So right now it currently just looks at the towers without considering that information, but this question kind of highlights on a point I rushed through about using more sophisticated post-processing, especially with our object detection model predictions, you have the predicted bounding box around the tile. So you can change that to a centroid for post-processing, and you can know that the towers should be about 50 to 100 meters apart, and they're only allowed to have X number of neighbors. Since it's connected in a grid, if you see like a large clump, that's probably a sign that there's false positives. But right now that's not built into the model, that's built into some post-processing steps we're trying to do. But if there's a way to build that into the model, that would be a lot more sophisticated and something really interesting to investigate.
That's great. That's great. And I will note there, folks interested in your work in the chat there and in Q&A. So please feel free to follow up with those. But let's take a moment to thank Martha. Martha, thank you so much for your talk. And we're going to move on to our next speaker now. And feel free.
Thanks so much for having us.
Oh, absolutely, absolutely. Thanks again, Martha.